Welcome everybody to this presentation. As we know, renewable energy being pollution-free, cheap, and conforms to the concept of sustainable development, they have gained considerable attention worldwide in the last 2 decades. And many countries have effectively integrated a large share of renewable energies into the primary grid, and a high penetration level is targeted for the next 3 decades. But it is already pointed out that this massive integration of renewable energy is detrimental to the system stability. So some form of mitigation scheme is required that has received significant attention to the researchers. In my today's presentation, I will highlight the problem associated with high level of renewable energy integration, mitigation techniques, proposed technique, simulation result, conclusion. The most promising renewable energies are solar and wind, which are generally connected to the grid through power electronics converter. Their interaction with the grid is different from the synchronous generator-based thermal unit. The inherent kinetic energy of the synchronous generator provides inertia to the grid, but this is not the case for converter-based system. The overall, it contributes zero inertia to the network. Thus, the overall system inertia is reduced. Since the system frequency is directly linked to the system total inertia, the renewable integrated system frequency control is badly affected. In the face of a small disturbance, a large frequency deviation will result. Also, the rate of change of this frequency deviation also will be higher. That will make that will trigger the under frequency delay, and that can provoke the separation or the tripping of sensitive loads and generators. So thus the system frequency control and the reliability are badly affected. So for the mitigation techniques, several mitigation techniques already proposed in the past, such as auxiliary load frequency control technique, inertia emulation technique, deloading technique, and droop technique, energy storage based system. Out of this, inertia emulation technique is considered the most effective one, and for the it is also considered that it will be the part of the coming renewable based system or the converter based system, integral part of the converter based renewable system. So in the inertia emulation technique, the inertia is virtually supported to the grid through energy storage and the inverter system through proper control system. Different types of energy storage system already proposed, like superconducting, magnetic energy storage system, supercapacitor, battery, fuel cell, flywheel energy storage system. And most of the work has been focused on the control techniques. Different control techniques has been proposed, both are not linear, non-linear, to improve the dynamic system performance. In my today's work, in this work, I am also proposing some improved control system for improving the system dynamic performance. The system we consider that is called the two-area system, where in each area there is a thermal unit, and there is a solar PV, industrial loads, and the energy storage system. So the frequency deviation signal from each area is collected to the control center, And also the tie line power deviation also is collected to the control center. And this control center provides appropriate control signal to the controller for the required control action. For the system dynamic modeling, adequate model has been considered for each component with required consideration of the constraints like deadband control and GRC, GDB, all this thing. And for the wind and solar, the variation of this is created through the white noise. And for the energy storage system, we have considered here SMEs is a superconducting magnetic energy storage system, which is modeled as the superconducting coil and a DC resistor. And the interaction of the SMEs and the grid is through the converter and the transformer. That is the SMEs in exchange power through this converter and this transformer to the grid. For the dynamic modeling or for the controller design, the SMEs system is modeled with the standard model. And here we are proposing the fractional order controller, because the fractional order controller recently has gained very good attention because of its superior performance compared to the integer order controller. The difference between fractional order controller and integer order controller can be depicted in this two figure. In the delta lambda axis, here the lambda is a real number. It could be from 0 to 2. So this is the transfer function for the fractional order PI controller. We are considering very simple PI controller, not PID. So for the integer controller, this lambda has only two distinct values, either 0 or 1. If it is 1, then it will form as a PI controller. If it is 0, it will form as a P controller or proportional controller. But for the fractional order controller, since lambda could be any value in between 0 to 2, so it gives the freedom for infinite tuning for better performance. And the controller parameters are optimized through wall optimization algorithm. Here already altogether there are 12 optimization parameters, and the cost function we are considering the frequency deviation in each area and the power tie line power deviation. So here is the convergence of the wall optimization algorithm. It shows that the objective function is converging within 30 iteration in each case. So that gives the indication that this algorithm, it is insensitive to the initial value and it is quite robust. So this is the system parameters for area 1 and area 2 that is used for this optimization. And this is the optimized parameters, 12 optimized parameter received from this optimization algorithm. These optimized parameters and the system parameters are used for the dynamic simulation of the system to test the performance of the controller for different scenarios like light load variation, heavy load variation, solar and wind power variation, and reduced inertia of the system. So this is the result for the step load change in area 1. If we apply 0.2, per unit, that is a light load in variation in area 1, then the response, frequency response, these are the frequency response for the area 1 and for the area 2. So from this frequency, we can see that without auxiliary controller, there is a large deviation or oscillation in the frequency. And with the conventional controller, the performance is quite better, quite acceptable. But with the proposed fractional order based superconducting, that is with the proposed controller, the performance is much better than the conventional controller for both area 1 and for area 2. Here, this is the result if there is a larger disturbance or the step load change is applied. That means if we apply 0.3 per unit load change in area 1, then we can see the system frequency variation increases and become unstable without an auxiliary controller. But with the conventional controller, the response is quite acceptable, but with the proposed controller, it shows much better performance than the conventional controller for both area 1 and area 2. And this is the, if we apply, that means 0.2 load change, step load change, or the disturbance in area 2. So this is the response in area 1 and area 2. So here again, we can see that with no auxiliary controller, the frequency deviation is quite high. With the conventional controller, this is the response, and with the proposed controller, this is the response. So the variation is very negligible and compared to the conventional controller. So this is the load profile variation for the step change, that is a frequency response for a step load change in area 2, that is 0.3 step load change. So we can see again that with the proposed controller, it is giving much better response than the conventional controller. So the response of the proposed controller also tested the multiple load variation to see how the system, the controller is responding to the multiple disturbance. So that means if a second disturbance or the subsequent disturbance is coming, then how it will handle this thing, or whether the system frequency deviation is reaching 0 before the next disturbance is coming. So we apply this kind of disturbance to area 1 and see the response for area 1 and frequency response for area 1 and area 2. So we can see that there is a large frequency deviation without auxiliary controller, and with the conventional controller, it is bringing back the system to the stable system with a acceptable variation limit. But with the proposed controller, it is giving much better result. And similarly, this kind of multiple disturbance is applied to, if we apply to the area 2 and look at the frequency response, frequency deviation response in both area 1 and area 2, we can again see there is that is the proposed controller is giving much better result. The controller also tested, the proposed controller also tested for wind and solar power variation. So for wind and solar power variation, this type of variation is considered. And here we are applying the solar power at this moment. And after some time, we added the wind power also. So we can see that without controller or the result of the controller, the variation, frequency variation is quite high. And with the proposed controller, this frequency deviation is very minimum. So compared to that is, it gives a better performance compared to the conventional and controller. System, this proposed system also tested for reduced system inertia. That means the system inertia in both area 1 and area 2 is reduced by 50%, and the 0.2 load variation is applied in area 1. So and area 2. So we can see that with this reduced inertia, the system is becoming unstable, but with the proposed controller, this system, that is the performance is very good compared to the conventional controller. So in conclusion, we can say that an improved load frequency control technique for low inertia power system is proposed. The inertia of the system is supported virtually. The system frequency deviation is greatly improved. It is also robust against parameter variation. It provides improved response with regard to the overshoot, undershoot, and settling time. The proposed approach endorses green effort to augment sustainability. That is the end of the presentation. If you have any question, you can ask me. I will be happy to answer. Thank you.